This is Chapter 5, Exponential Functions and Logarithmic Functions. Section 5.1, Inverse Functions. This takes care of a final little topic about functions that was not covered earlier in the book. Inverse relations. Okay, we're going to do this kind of the way we did functions. We don't need to do the Cartesian products. Remember that listed all possible ordered pairs. So we're going to start off with the relations. The basic idea of an inverse function or inverse relation is to undo whatever the function or relation has done. For example, if a function multiplies numbers by 2, the inverse would divide numbers by 2. Okay, students sometimes think of it as the opposite, but remember the technical name is inverse. Some ordered pairs for the function might look like this: 1, 2, 4, 8, x, and 2x. Remember, our function is doubling. So whatever x is, or the x coordinate is, the y coordinate will multiply it by 2. The corresponding ordered pairs for the inverse would look like this: 2, 1, 8, 4, 2x, and x. Because remember, the inverse would divide by 2. So 1 is 2 divided by 2, 4 is 8 divided by 2, and x is 2x divided by 2. Notice how the ordered pair xy became yx. We basically just switched the role of x and y. Definition. The inverse of a relation is a set of ordered pairs found by interchanging x and y. That's all you do. To get the inverse relation, just switch the ordered pair x and y. Make x become y and y become x. The definition also applies to finding the inverse of a relation if the relation is given by an equation. So to find the inverse of a relation, we have an equation. Again, just switch x and y. That's all there is to it. It's not a trick. Find the inverse of each relation. Here's our first one. My relation R is the set of ordered pairs 1, 10, 3, negative 7, and 6, 11. Okay, remember the inverse? You just switch the ordered pairs x, y, make them yx. So it would be 10, 1, negative 7, 3, and 11, 6. Don't forget the braces around the set of ordered pairs. Remember, it is a set. Number 2. My relation S is the set of ordered pairs capital M, little m, capital T, little t, capital Q, little q, capital R, little r. The inverse, again, just switch the x and the y. So the little letters would come first in the inverse. So the inverse of S is going to be little m, little t, capital T, little q, capital Q, little r, capital R. That's all you're doing. Switch the ordered pair x, y, make it yx. I have the equation x squared y to the 4th minus 7x plus 3y to the 6th minus 10 equals 7y. Remember, to get the inverse relation, just switch x and y. So where we see an x, put a y. Where we see y, put an x. So the inverse would be y squared x to the 4th minus 7y plus 3x to the 6th minus 10 equals 7x. Again, we just replace the x's with y's and the y's with x's. Don't do anything else to it. Leave it alone. Don't make it more difficult than what it is. Number 4. My equation is 5x minus 7y to the 4th plus 6y squared x cubed is equal to 12xy minus 17. Okay, once again, to get the inverse, just switch the x and the y. Replace all the x's with y's and all the y's with x's. So my inverse relation would be 5y minus 7x to the 4th plus 6x squared y cubed equals 12yx minus 17. And once again, don't do anything else to it. You're done. That is the inverse relation. The horizontal line test. Remember, for functions, we had a vertical line test. If we're switching x and y's, vertical becomes horizontal. So recall that a function is not allowed to reuse its first coordinates. This led to the vertical line test for functions. We would like for the inverse of a function to also be a function. Since we now know that to find an inverse relation, we simply switch x and y, this leads to part A, the horizontal line test. If no horizontal line intersects a graph at more than one point, then the inverse of the graph is a function. So again, if no horizontal line intersects the graph at more than one point, then the inverse of the graph is a function. If the inverse is a function, then we say that the graph has passed the horizontal line test. Let's try some examples now. If the inverse is not a function, then we say that the graph has failed the horizontal line test. Just like with the vertical line test, passing meant it was a function, failing meant it wasn't a function. So for the horizontal line test, passing means the inverse is a function, failing means the inverse is not a function. So some examples. Determine whether or not the inverse of each graph represents a function. So here's number 1, the circle. Okay, notice the circle itself is not a function. Neither is its inverse, because here's a horizontal line, namely the x-axis, that intersects the graph in 2 points. So the inverse is not a function. Number 2. a parabola. Now remember, a parabola itself was a function, but the inverse, notice here is a horizontal line, again the x-axis, that hits the graph in more than one point. So the inverse is not a function. Number 3, a line. Remember, the only line that wasn't a function was a vertical line. So here the inverse is a function because it passes the horizontal line test. Notice the only line which would fail the horizontal line test is a horizontal line. Parabola on its side. Okay, the inverse, there is no horizontal line that hits the graph in more than one point. The inverse itself is a function, even though the original parabola on its side is not. So the inverse is a function. Now, notice if a graph represents a function, then it must pass the vertical line test. If the inverse of the graph is a function, then it must pass the horizontal line test. We would like to have a function do its inverse and still have a function. We want to start with a function, find its inverse, and still have a function. So this leads to one-to-one functions. Definition. A function that passes both the vertical line test and the horizontal line test is called a one-to-one function. This is how, the way to look at it graphically. Okay? If you can pass both the vertical line test and the horizontal line test, that's one-to-one. Some facts. Only functions that are one-to-one have inverses that are functions. Now, if you recall our examples that we had, only the line was the example that we had where it was a function and so was its inverse. Now, there are other functions besides lines that are one-to-one. In our previous set of examples, again, on the example 3, remember that was the line, was a one-to-one function. For ordered pairs, if all first coordinates are different and all second coordinates are different, then the set of ordered pairs represents a one-to-one function. Again, we're taking the point of view that we will not list the same ordered pair twice. So if all first coordinates are different and all second coordinates are different, then you have a one-to-one function, which means that its inverse will also be a function. Remember, only the one-to-one functions have inverses that are also functions. Finding an inverse function. Okay, we already know how to find an inverse relation. You just switch x and y, and that's all you do. After you switch x and y, you leave it alone. With an inverse function, there's a little more work to do. So, the notation. Let f be a function whose inverse is also a function. We denote the inverse of f by this thing, f with a superscript of -1, and it's read f inverse. Warning, never read f inverse as f to the -1. It should always be read as f inverse. F to the -1 means something entirely different. The method for finding f inverse. That is a minus sign. The f seems to have eaten the minus sign, so probably should have put a space there so we could see it. You'll be given a formula for f of x. You will then be asked to find a formula for f inverse of x. Here's your method. Step 1. Replace f of x with y. So you start off with f of x equals something. You now have y equals something. So you've basically converted a function into an equation, which means you now have a relation. Step 2. Interchange x and y. What you have done now in step 2 is you found the inverse relation. Now you got to do a little more work. If you were just looking for the inverse relation, you would stop right there. Step 3. Solve for y. This is where all the work is. So after step 2, you'd have x equals something. After step 3, you work, and you end up with y equals something new about x. Now it's possible that a function is its own inverse. So don't be alarmed if after step 3 it looks like what you started with. Then step 4, replace y with f inverse of x. Remember, you are looking for a formula for f inverse of x. So be sure you write f inverse of x equals whatever. Sometimes in my math lab, the f inverse of x will already be sitting there with an equal sign, and you're just filling in the right-hand side. So pay careful attention to what it is you're supposed to write. Some examples. We want to find a formula for f inverse of x for each of the following. Here's our first one. I've got f of x equals 4x plus 7. Remember, this is a line. It's not a vertical line, it's not a horizontal line, so it is one-to-one. Step 1. We're going to replace f of x with y. So I'm starting with f of x equals 4x plus 7. When I replace f of x with y, I will have y equals 4x plus 7. Okay, step 2, I'm supposed to interchange x and y. So I'm going to have x equals 4y plus 7. I'm now going to take this equation and solve it for y. Now notice, since y is on the right-hand side, I'm going to keep it there. So first, I'm going to get rid of this 7. So we're going to subtract 7 from both sides. Now divide everything by 4. So I'll have x minus 7 all over 4 is equal to y. If you want to, you can do like I did here. Have 1/4 x minus 7/4 is equal to y. That way you can actually see the m, the slope, and the y-intercept of -7/4. Okay, so we've completed step 3. Remember step 4, replace y with f inverse of x. So I'm going to have 1/4 x minus 7/4 is equal to f inverse of x. Again, we like to have the function on the left, so let me just switch the ordering and have f inverse of x equals 1/4 x minus 7/4. There's your final answer. Now again, you could also write it as x minus 7 all over 4. Your choice. Example 2. F of x equals 3x squared minus 7, and x is greater than or equal to 0. Okay, this restriction that x be greater than or equal to 0 is just to ensure that this function is 1-to-1. Remember, this is a parabola, and the parabola failed the horizontal line test. By saying x is greater than or equal to 0, that's actually the right side of the parabola. You don't really need to worry about this when you do your work. Okay, this is just to make sure that you're 1-to-1. So again, we're starting with f of x equals 3x squared minus 7. Remember, step 1, you're supposed to replace f of x with y. So I'm going to have y equals 3x squared minus 7. Step 2 was to interchange x and y. So I'm going to have x equals 3y squared minus 7. We then take that equation and solve it for y. Again, y is on the right-hand side. I'm going to leave it there. So first, let's add 7 to both sides. So I'll have x plus 7 is equal to 3y squared. Okay, now we're going to divide everybody by 3. So I'm going to have x plus 7 all over 3 is equal to y squared. Okay, I now have something squared as a number. We're going to take square root. Okay, we don't need to put the plus or minus. Okay, the restriction right here is what prevents us from having to do that. So taking square roots, I'm going to have the square root of x plus 7 all over 3 is equal to y. We now have it solved for y. You don't need to rationalize the denominator. Please don't do that. So now all we've got to do is replace y with f inverse of x. So I'll have the square root of x plus 7 all over 3 is equal to f inverse of x. And again, we like to have the function on the left, so we're going to write it as f inverse of x is equal to the square root of x plus 7 all over 3. Number 3. I have f of x equals 5x cubed plus 11. Okay, we go through the same process. Again, we're starting with f of x equals 5x cubed plus 11. Remember, replace f of x with y. So y equals 5x cubed plus 11. We then interchange x and y, have x equals 5y cubed plus 11. We want to solve this equation for y. Again, y is on the right, so I'm going to keep it there. So first, let's subtract 11 from both sides. So I'll have x minus 11 is equal to 5y cubed. Okay, we divide everybody by 5. So I'll have x minus 11 all over 5 is equal to y cubed. Okay, to undo the cube, we take cube roots of both sides. I'm going to have the cube root of x minus 11 all over 5 is equal to y. Now replace y with f inverse of x. So I'm going to have the cube root of x minus 11 over 5 is equal to f inverse of x. And again, we like to have the function on the left, so our final answer will be f inverse of x is equal to the cube root of x minus 11 all over 5. And again, please do not rationalize the denominator. It's extra work to accomplish nothing. Number 4. I have f of x equals 3x plus 2 all over 5x minus 7. So again, we start with f of x equals 3x plus 2 over 5x minus 7. Remember, step 1, replace f of x with y. So y equals 3x plus 2 all over 5x minus 7. Step 2, we were to interchange x and y. I'm going to have x equals 3y plus 2 all over 5y minus 7. This is the equation we want to solve for y. Okay, I have a fractional equation. My common denominator is 5y minus 7. So I'm going to multiply by 5y minus 7. Now some students, they'll think of this x as x over 1, and then they'll just cross multiply. It's the same thing. We're going to multiply both sides of the equation by 5y minus 7. So I have x times 5y minus 7 is equal to 3y plus 2. And again, remember, we're trying to solve for y. Y appears on both sides of the equation. So on the left-hand side, I have to distribute that x. So I'm going to have 5xy minus 7x is equal to 3y plus 2. So I just distributed the x. I now want to get everything with a y on one side of the equation and everything that doesn't have a y on the other side of the equation. I'm going to move all my y expressions to the left. So this guy, 5xy, stays there. 3y gets subtracted and comes over here. If it doesn't have a y, I'm going to move it to the right. So the 2 stays where it is. I'm going to add 7x. So again, anything with a y goes to the left side of the equation. If it doesn't have a y, go to the right side of the equation. I have 5xy minus 3y is equal to 7x plus 2. Now, before when we were solving equations, we would just say, combine your similar terms. Okay, here I can't really combine them, but I do want to figure out the coefficient of y. So on the left-hand side, factor out y. So factor y from each of the two terms on the left-hand side. So I have y times 5x minus 3 is equal to 7x plus 2. So again, we've just factored out the y. Now to solve for y, we divide by the coefficient of y. The coefficient is 5x minus 3. So we're going to divide both sides by 5x minus 3. So y equals 7x plus 2 all over 5x minus 3. We finally completed step 3. We finally got y equals. Now remember step 4, replace y with f inverse of x. So f inverse of x is equal to 7x plus 2 all over 5x minus 3. Notice the inverse does look very similar to the original function. Again, sometimes it is possible for a function to be its own inverse. The classic example of a function that is its own inverse is f of x equals 1 over x. It is its own inverse. Okay, the graphs of f and f inverse. Now, of course, if you're given their formulas, there's no reason that you couldn't just give it to your graphing calculator and have it graph both of them. So our finding the graphs of f and f inverse is going to involve something a little bit different. So we want to be able to sketch the graph of y equal f inverse of x if we were given the graph of y equal f of x, not the formula, but the graph itself. Now, what we're about to look at is actually more of an artistic skill rather than a math skill. Recall, a function's relation. To find an inverse relation, we just switch x and y. Graphically, this means that the graph of y equal f of x and y equal f inverse of x are reflections of one another through the line y equal x. Okay, the line y equal x is a line that goes through at a 45-degree angle. It goes through 0, 0, 1, 1, 2, 2, 3, 3, and so on. So this reflecting thing through the line y equal x, again, it's more of an art skill than a math skill. Remember, we covered reflections through the x-axis and y-axis way back in chapter 2. Okay, the line y equal x, again, is a line that makes a 45-degree angle with the positive x-axis. It cuts the first and third quadrants in half. Okay, we usually sketch it as a dotted line to help us do the reflection. It's not really part of our answer, but it helps us to get the answer. Some examples. Given the graph of y equal f of x, sketch the graph of y equal f inverse of x. Again, no formula will be given. We're just going to try to get it from the graph. Okay, so here's my y equal f of x. Notice it does not go on forever. It's just this little curvy segment here. I do have some points labeled, -2, 0.25, and 2, 4. This point I didn't label, but hopefully you can see that it is the point 0, 1. Okay, the first thing we do to sketch the inverse is we draw the line y equal x. Remember, it goes through 0, 0, 1, 1, 2, 2, 3, 3. So there's the line y equal x. The idea is we want to reflect this curved blue segment through that red dotted line. Again, now the points that we know, we can graph them by simply switching the x and the y. So the -2, 0.25, if I switch x and y, it becomes 0.25, -2. This point, 2, 4, becomes 4, 2. Okay, now does this thing kind of bows in toward the line y equal x? This will kind of bow in toward the line y equal x. Now this point, 0, 1, should reflect to be 1, 0. So I'm going to try to connect those with some sort of curvy thing there. Now it's supposed to be that if you fold along the dotted line y equal x, the blue graph and the red graph will coincide. Again, it's more of an art skill than a math skill. Number 2. Okay, I've just got this little segment. I didn't label my points, but I hope you can tell what they are. This is the point -1, -2. This is the point 3, 5. Okay, so the function itself is just that little segment. Okay, first we draw the line y equal x. Remember, it goes through 0, 0, 1, 1, 2, 2, 3, 3, and so on. Okay, again, these points that I've put the dot with, the -1, -2, and the 3, 5, we switch their x and y to figure out where the points for the inverse will go. So -1, -2 becomes -2, -1. All right, just switch x and y. This point 3, 5 will become 5, 3. And now just connect those two dots. And that will be the graph of y equal f inverse of x. And again, it's supposed to be if you fold along the dotted line y equal x, the red graph and the blue graph will match. The last thing we look at are what are sometimes called the defining properties of f and f inverse. So the properties of f and f inverse. Number 1, f of f inverse of x is equal to x. It's kind of like you start with x, you apply the inverse and apply f, you're back to where you began. Remember, the function and its inverse undo one another. Number 2 says f inverse of f of x is equal to x. Again, you do a function followed by its inverse, you're back to where you began. These two are saying that the two f and f inverse undo one another. And this is what you're supposed to do to verify that a given function is in fact an inverse of another function. Let's look at the compositions. Number 3, the domain of f is the range of f inverse. Number 4, the range of f is the domain of f inverse. 3 and 4 are saying that the domain of one is the range of the other. Okay, let's try to apply these two little properties. It's actually 1 and 2 we're going to worry about. So some examples. Number 1 says, let f of x equal the cube root of 7 times x minus 12 all over x cubed plus the square root of 22. Find f of f inverse of pi. Here you're probably looking at it and saying, I don't really want to do that. That's going to be too difficult. Whenever something looks like it's really nasty, there must be some sort of trick you're supposed to do. Notice you're doing a function followed by its inverse. So you're supposed to end up with where you began. So by property number 1, f of f inverse of pi is pi. You started at pi, you apply the inverse in the function, you end at pi. Remember, the function undoes its inverse, the inverse undoes the function. Number 2, let g of x equal pi x minus the square root of 43 all over x minus 16. We want to find g inverse of g of the square root of 7 over 9. Now again, it looks pretty horrible. It looks like something you don't want to do, but again, we're doing a function followed by its inverse. So according to property number 2, g inverse of g of the square root of 7 over 9 is the square root of 7 over 9. Again, if you do a function followed by its inverse, you end up with what you began with. If to kind of give you a loose looking at this, you don't see an exponent with this g. It's understood to be 1. If you think about the law of exponents, negative 1 plus 1 is 0. So you have g to the 0 power, which is 1. So a lot of students think of, oh, I just have 1 times the square root of 7 over 9. Yeah, that's what you have, which would be the square root of 7 over 9. That is the end of section 5.1.